Hey guys, welcome to my channel. China is known for its long history and its rapidly growing economy. But what truly astonishes the world is something else entirely. Its almost unbelievable speed of construction. From massive infrastructure projects that cross mountains and seas, to skyscrapers that rise straight into the clouds, China is reshaping how humanity understands what it means to build. The question is, how is all of this even possible? And what does this pace of construction really mean for the future? In recent years, China has pushed engineering to its physical limits through a series of mega projects. Gigantic dams operate safely in some of the most complex geological environments on Earth. Ultra-long tunnels cut through fault zones and high mountains. Suspension bridges span deep valleys, turning what once seemed impossible into everyday reality. These projects are not only massive in scale, they are completed at a speed that continues to surprise even experienced engineers. High-speed rail networks, multi-lane expressways, and cross-sea bridges emerge one after another. This is not coincidence. It is the result of advanced engineering technologies, a highly integrated industrial system, and an execution capacity that few nations can match. Some view this pace with admiration, others view it with skepticism. So how does China transform blueprints into reality so quickly? What systems, decisions, and trade-offs lie behind the steel and concrete? In this video, we go deep inside some of the world's most extreme engineering projects to uncover the real forces shaping China's mega construction era. Across China's 9.6 million square kilometers of land, more than 45,000 tunnels now cut through mountains, rivers, cities, and coastlines. Together, they form a vast high-speed circulation network, moving people and goods north to south, east to west, with unprecedented efficiency. If all of these tunnels were connected end-to-end, their combined length would stretch more than once around the Earth. From towering mountain ranges to deep rivers, from dense megacities to the open sea, China's tunnel construction has reached a scale that commands global attention. It marks a historic shift, from following the world's engineering leaders to setting the pace itself. China's reputation as an infrastructure powerhouse is not built on size alone. It comes from a willingness to take on projects that most others consider impossible. In northwestern China's Gansu province, there is one such project, a tunnel that pushed the limits of modern engineering, the Humaling Tunnel. The tunnel is only 173 meters long, yet those 173 meters defeated engineering teams around the world. Even Germany, renowned for its tunneling expertise, eventually withdrew. China did not. After 6 long years, one of the most difficult tunnels ever attempted was finally completed. So what made the Humiling Tunnel so extreme? The challenge was not hard rock, it was instability. The tunnel passes beneath a reservoir and a river, leaving the surrounding ground permanently saturated with water. The soil is primarily loess, a loose, porous material known for collapsing and liquefying when disturbed. Construction here was like digging through quicksand. Once excavation began, the surrounding soil shifted, cracks spread, and collapses became a constant threat. Even the smallest disturbance could trigger structural failure. Heavy rainfall made conditions even worse. Water infiltration weakened the ground further, turning every working day into a potential disaster. Here, every meter forward was a calculated risk. When conventional methods failed, China invited international experts to assess the problem. But one after another, specialists examined the loose loess and water-saturated ground and found no solution. There was no proven technique, no reliable precedent. The Humiling Tunnel soon became a symbol of engineering limits. It was even mockingly nicknamed the Tofu Tunnel, not because of poor workmanship, but because the ground itself was dangerously fragile. Yet Chinese engineers refused to abandon the project. They developed an exceptionally cautious construction strategy, advancing in small sections, combining step-by-step excavation with continuous vacuum dewatering to stabilize the soil, minimizing disturbance wherever possible. The work was hazardous. Sudden water and sand inflows were frequent. Progress was painfully slow, on average, only 2 to 3 meters per day. A workforce of more than 1,200 engineers and workers rotated through the site for over 6 years. During winter, dedicated teams were tasked with breaking ice to prevent the saturated soil from freezing, a condition that would have completely halted construction. This was a test of endurance, precision, and resolve. In the end, persistence paid off. The Humiling Tunnel was completed. News of its success quickly spread through the global engineering community. It was not a massive structure, but it became a powerful symbol of Chinese engineering capability. Proof that extreme challenges do not always demand retreat. The tunnel closed a critical gap in the Humiling Railway, a vital corridor linking the Yellow River and Yangtze River regions. Its completion restored transportation continuity and helped stimulate trade and tourism along the route. The Humiling Tunnel is short, but its significance is anything but. It demonstrates a fundamental truth of modern engineering. The true limits are not always defined by geology or technology, but by whether people are willing to persist to the very end. The Humiling Tunnel is only 173 meters long, yet it proved one crucial truth. When geology refuses to compromise, engineering has only one choice: persistence. But what happens when difficulty no longer comes from fragility, but from the limits of length, depth, and scale? What if a tunnel does not merely pass through a mountain, but almost slices through an entire mountain system? What you are about to see next is the same spirit, magnified to its absolute extreme. How long is 22.1 kilometers? If you stood it upright, it would stretch from the summit of Mount Everest straight down to the deepest point of the ocean, or from the surface of the Earth, it would punch directly through the Earth's crust. And that is the length of the world's longest highway tunnel. This is the Tianshan Shengli Tunnel, located in Xinjiang. On December 26, 2025, the tunnel will fully open to traffic. For the first time in history, China will cut completely through the Tianshan Mountains with a continuous expressway. Now let us witness this historic moment together. But the question is unavoidable. How difficult is it to build a highway through the Tian Shan Mountains? What truly happens beneath mountains that plunge more than 1,000 meters deep? If it were you, how many challenges could you survive? What you are looking at now is a gap along the ridge of the Tianshan Range, but it is not natural. More than 60 years ago, in 1957, engineers used tons of explosives to blast a passage directly through the mountain. It became known as the Lahuko. Only through this opening could National Highway 216 cross the Shengli Pass, becoming the first road to connect northern and southern Xinjiang. Yet the winding mountain roads meant that a straight-line distance of just over 250 kilometers had to be stretched to nearly 400 kilometers. In winter, heavy snow sealed the mountains shut, turning travel into a life-threatening risk. Even detouring around the Tian Shan range, the journey between Urumqi and Korla took more than 7 hours. In eastern China, that same distance could take you from Beijing all the way to Shanghai. Want something faster? There was only one option: go straight through the mountains. But tunneling through a mountain is not about choosing any location. Too low, and the tunnel would become absurdly long. Too high, and steep gradients and winter snow could not be avoided. After repeated analysis and trade-offs, engineers made their decision. Right here, they would build a 22.1 kilometer tunnel, 4 kilometers longer than the previous record holder, the Humiling Tunnel. Choosing this length meant only one thing: challenge after challenge was unavoidable. The first obstacle was time. Using conventional drill and blast methods, even with excavation from both ends, construction would take at least 10 years. By adding adits or incline shafts and working in parallel, the timeline could be shortened to 72 months. But engineers chose to go even faster. Between the two main tunnels, they built an advanced pilot tunnel, also known as a parallel service tunnel. Compared with excavating adits through steep mountain slopes, this approach was shorter, safer, and more controllable. As a result, the 22.1 kilometer tunnel was divided into 15 construction sections. At peak periods, as many as 14 work faces were operating simultaneously. This strategy became known as a super long tunnel, built in ultra-short segments. But there was one condition: the pilot tunnel had to advance faster than the main tunnels. How was that achieved? The answer was China's independently developed hard rock tunnel boring machines, Tian Shan and Shengli. Their cutter heads measure 8.43 meters in diameter, capable of efficiently crushing hard rock at speeds 3 to 10 times faster than traditional drill and blast methods. They were perfectly suited for excavating the pilot tunnel. The two main tunnels, however, with diameters reaching 14 meters, far beyond the limits of conventional TBMs, were excavated using drill and blast techniques instead. In just 52 months, the entire 22.1 kilometer tunnel was completed. The pilot tunnel and adits were permanently retained, serving as emergency and rescue passages. But this 22.1 kilometers was never an easy journey. Once you truly cut into the Tianshan Mountains, you discover just how fragmented they are. 10 different rock types, 17 fault zones of varying size. The largest, the Boa Fault, is a staggering 460 meters wide, almost splitting the northern and central Tian Shan ranges apart. Facing such unstable geology, alternating between hard and soft, intact and shattered, conventional TBMs reached their limits. Engineers had no choice but to upgrade the Tian Shan and Shengli machines in unprecedented ways. In normal mode, the machines used gripper shoes to brace against solid rock walls, generating thrust without additional support. In difficult mode, steel frames were installed first, followed by concrete backfill to stabilize the tunnel. And in hell mode, where rock deformation and collapse risk were extreme, the machines provided full circumferential support, similar to shield tunneling, but using steel structures stronger than concrete. Even when the machines became trapped in complex strata, crews could detour through the main tunnel to reach the cutter head and conduct emergency rescue operations. Eventually, the opposing TBMs achieved millimeter-level alignment, and the pilot tunnel was fully connected. Inside the main tunnels, engineers adopted a different philosophy, using flexibility to overcome rigidity. Foamed concrete was injected into nearly 40,000 PE pipes and wrapped along the tunnel walls, forming a 70-centimeter-thick shock-absorbing layer. In the reinforced concrete lining, a 1-meter-wide deformation joint was deliberately left every 30 meters. This allowed the tunnel to behave like a segmented staff, flexible, resilient, and capable of absorbing fault displacement without catastrophic failure. Even after breakthrough, another challenge remained: ventilation. Direct fan ventilation is effective for only about 5 kilometers. To solve this, engineers sank 4 vertical ventilation shafts from the mountain peaks, dividing the 22.1-kilometer tunnel into 5 independently ventilated sections. The deepest shaft reaches 707 meters, taller than China's tallest skyscraper. How do you dig a shaft that deep? By standing a TBM upright. Thus was born the world's first vertical hard rock boring machine, Shuchuang. Combining TBM technology with oil drilling systems, it can drill a vertical shaft 11.4 meters in diameter with fully unmanned operation. Today, we no longer need the sacrifice of heroes to make pathways through mountains. Yet the challenges were still not over. The tunnel portals sit at elevations near 3,000 meters. Average annual temperatures are minus 5.4 degrees Celsius, with winter lows dropping below minus 40. Without proper thermal protection, ice could disrupt traffic and even damage the structure. Beyond insulation, engineers installed something unexpected: heating. They discovered that temperatures deep within the mountain remain stable. By drilling down 80 meters, they tapped into geothermal heat and circulated it through heat exchange pipes embedded in the tunnel lining, providing continuous, stable warming. How many challenges have you passed so far? In reality, builders also had to confront spoil disposal, wastewater treatment, ecological protection, geological surveys, emergency rescue systems, and fire prevention. Only after overcoming all of this was the world's longest highway tunnel completed. With its opening, the first Tian Shan Expressway was born. Travel time between Urumqi and Korla was cut from 7 hours to just 3. Combined with the under-construction Duku Expressway and the Zhaoan Highway, Xinjiang is forming a truly integrated highway network. From here, 3,000 kilometers eastward reaches any city in China. 3,000 kilometers westward opens the gateway to Central Asia. Thus, the ancient passage through the Tianshan Mountains, thriving since the Han Dynasty, fading after the Song, is finally reclaiming its former glory. If the Tianshan Shengli Tunnel answers the question, how do you safely carve a 22.1-kilometer corridor through extreme mountains? Then the next question is inevitable. What happens when tunnels leave the mountains entirely and enter the underwater world? Mountains are at least stable. Water never is. In China, the answer does not lie only beneath the sea. It also lies beneath a seemingly calm inland lake, Taihu, the Taihu Lake Tunnel. Its true challenges were never about length. They came down to 3 words: alignment, backfill, buoyancy. Alignment comes first. In mountain tunnels, errors can still be corrected. In immersed tunnels, alignment happens only once. Each segment is nearly 100 meters long, weighing tens of thousands of tons. They are not dropped into the water. They are lowered, or slowly, precisely, balanced between buoyancy and water pressure. The allowable error is measured in millimeters. If the angle is wrong, if the position drifts, there is no rework. The entire segment is scrapped, which means engineers must calculate everything in advance. Water currents, thermal deformation, and subtle buoyancy changes caused by fluctuating water levels. At Taihu, there is no align first, adjust later. You get one chance, and it must be right. Then comes backfilling. Alignment does not end risk, it begins it. The lakebed is not bedrock, but water-saturated soft clay. Uneven backfill leads to differential settlement, concentrated stress, and long-term structural fatigue. These problems do not appear immediately. They emerge after 10, 20 years. So backfilling is not about filling space. It is about layering, zoning, density control, and calculating long-term consolidation settlement. Here, the question is no longer construction difficulty. It is this: will what you build today survive time itself? Finally, buoyancy. Water is always trying to push the tunnel upward. Taihu is shallow, but shallow water combined with thin cover creates stronger uplift forces. If the tunnel loses restraint, the lake will try to lift it. Engineers must solve three things simultaneously: increase self-weight, use backfill to generate counterforce, and manage long-term water level fluctuations. This is not a one-time design. It is a decades-long struggle. The tunnel is not finished when construction ends. It must resist upward forces for generations. Seen together, Humaling Tunnel faced unstable loess and groundwater. Its solution was patience. Tianshan Shengli Tunnel faced extreme length and fractured geology. Its solution was systematic risk decomposition. Taihu Lake Tunnel faced irreversible underwater conditions. Its solution was absolute precision. None is harder than the others. They are simply different answers to different extremes. These tunnels were not built to prove they could be built. They exist for one reason: geography left no alternative. When mountains block the way, humanity tunnels through. When water divides the land, humanity goes beneath. China's engineering story is not only about speed or scale. It asks one enduring question: when conditions are at their worst and forward is the only option, can you accept the consequences? This is not a question of concrete or steel. It is a question of civilization, how it confronts geography, time, and risk. And that choice is still being made. Now that you've seen all this, what do you think of China's tunnel building technology? Let us know your thoughts in the comments below. And don't forget to subscribe to the channel. We'll see you in the next video.